start? DQ2. You got it. Because I didn't really pick, what did I really pick? I picked a little piece of some little bitty piece of the line of charge. Okay? And that little piece of charge occupies a little bit of line. Okay? Now, the interaction of that little piece of charge on that little piece of line that I picked tells me about a little piece of the energy of that whole line in that charge. Okay? Everybody with me? So now we have figured out, or at least sort of figured out, the energy between this little dq and this q. Yay! Now we have to do all the others. And how many more of them are there? Infinite.
Is that why you do integrals?
Well, that's how we eventually get there. Unfortunately, you're not quite there yet. All right, so let's do the easy part next. I'm going to see if you can handle this. I'm going to make a big step on you here. You ready? Shoo!
You took R, you replaced R.
Yeah, that was a joke. That wasn't really a big step.
How did that happen?
Okay. Now, oh, you ain't seen sorcery yet. Now, I have to add up all these charges, right? The effect of all these. Do the integral, but it's really adding up every little possible little dq interacting with this little q. Never lose sight of that. The minute you do is the minute you will not be able to do these. However, that's a lot easier said than done. Because don't write this. Everybody with me?
Yes.
Your first inclination is to do that. Because we've got to add them up. And adding them up is an integral. Unfortunately, you can't do that. Because this one, I'm almost guarantee you they didn't teach you in your calculus class whether you had it with Holly and I or some other way. You can't do this integral. I'm not saying you don't know how. I'm saying it can't be done. Because what they didn't teach you, or they should have, is what are our two kinds of, we have four units that define everything else can be written in terms of. What are they?
Addition, subtraction.
Meters, seconds. And what were the other two? Kilograms and?
Hour.
Coulombs. These two are called what? No. State variables. Where you're at, what time you were there, remember? Well, from now on, remember? Okay, the state variables, meters, and seconds. You can only integrate over state variables. Yeah, you can't integrate over coulombs because that is not a state variable. The only thing you're allowed to integrate over is state variables. So this has to be either like a dx, dy, or a dt.
Meters, seconds, kilograms.
Okay, everybody with me? I know they didn't teach that in calculus because I've never seen a calc book ever mention that. Okay, but mathematically, you can only integrate over state variables, things that have units of meters or things that have units of seconds. That's it. So this side doesn't work, does it? Because this is a little, the d something here is not in meters, it's in coulombs. What? Do you have a question back there?
Oh, I wasn't sure if you said state variables or not.
State, meters and seconds. Okay? Now, so what we have to do is somehow figure out how to take dq2 and turn it into something that involves a state variable. Okay? This is where I believe the voodoo magic comes into play. Okay? Now this little piece of Q occupies how big? A little piece of what?
Why?
Y.
Why?
Everybody with me?
Yeah.
That little piece of Q occupies a little piece of Y. Okay? I'm going to write something, and please don't spout out anything. Now, I wrote dq2 over dy. Now tell me what your first inclination to say is. What's that look like? Derivative, thank you. Okay. Now, banish that from your brain. Because that is not a derivative.
Yeah.
Because q is not a function of y. Q is a variable. It's a little piece of charge. Okay? It's saying that we have a little piece of charge
On Y.
occupying a little piece of
Y.
y. That is not the same thing as a derivative. Okay? So here's one of those classic cases of you have to understand what you're doing, or you're going to look at this and call it a derivative. When that's not what it is. It's saying that this little piece of charge occupies a little space of y. Because d something doesn't mean derivative. It means a small piece. Okay? This isn't telling you to take the slope of something. Okay? It's a little piece of charge occupies a little space in y. Okay? Everybody okay with that? Now, here's where I'm going to change gears for a moment. Okay? So we're going to kind of leave that problem right there for a second and see if you understand one other idea. Okay? So I'm kind of going to draw a line here because this is a side note that's not a side note, but it is a side note. Okay? What does that mean? And be careful, because you can probably guess when I ask a simple question. It's not so. Yes?
How many particles in an area? Or in a volume?
Which is it?
Volume.
Wrong, but thank you for playing. Still wrong, but thank you for playing.
How many particles in one place?
I'll give you. No, but thank you for playing. What? Somebody said something back there.
The amount of mass in a volume.
No, but thank you for playing. I didn't say mass density, I said density. All of you are trying to do either particle density or mass density. I didn't write particle density, I didn't write mass density, I wrote density. Does that make sense to everybody, first of all?
How many
charges in one place?
I didn't say charge density.
How much of something?
Yes.
How about I don't know?
That's probably the best answer I've heard so far, but okay.
How many of something occupies?
Okay, keep going. It's good so far. Start over again and stay. Nope. Start over.
Okay, how many of something occupies?
Stop. How many of something? We don't know what it is. It could be how much mass. It could be how much charge. Could be how many particles. It doesn't really matter. It's how much of something occupies. Now that's where I cut you off. Okay? Does that make sense to everybody? I'm having you stop there because you guys earlier were trying to say, well, it's area, it's volume. It's neither, but it's both. Because you can have how many charges occupy a line. You can have how many charges occupy an area. You can have how many charges occupy a volume. There's not a single form of density. There's linear density, there's area density, and then there's volume density. Okay? How many charges occupy a line would be what kind of density? Linear. How many charges occupy an area would be area density. Okay? How many charges occupy a volume would be volume density. Okay. What? Which is the one you're most familiar with, but unfortunately, all of them are perfectly valid. So, In terms of charge density, there are three versions. We just went through them. Linear charge density, which we denote with the symbol lambda. Congratulations, today is the beginning of your knowledge of the Greek alphabet. Okay, you had one last semester from you, if you remember that, the coefficient of static friction, the coefficient of friction. Okay, by the end of the semester, you might as well memorize the rest of the Greek alphabet. Okay?
I'm meaning to do that.
Okay?